All right, today we are going to talk about the technique of source transformation. And to understand why we can perform this transformation, we are going to talk briefly about electrical equivalence. So if we have this simple system, all right, where we have a voltage source and we connect to that voltage source, could be a current source as well, but we'll get to that in a minute, some arbitrary load. I'm going to call this resistance RL. We will observe a voltage drop across our load, VL, and a current flowing through our load, IL, such that there is some power absorbed by our load, which is just PL is equal to VL times IL using our power equation. Okay. So now let's consider two circuits. This one over here on the left contains a resistor R1. This one here, contains a resistor R1 in series with a resistor R2. And a circuit on the right containing the same voltage source only contains some resistance R3. So under what conditions are these circuits electrically equivalent? They are electrically equivalent if the voltage drop across the combined loads is equal on both sides. The current flowing through the load is equal on both sides. And the power absorbed by the load is equal on both sides. So what are the conditions for electrical equivalence to occur here? RL just needs to be R1 plus R2, right? We've been dealing with electrical equivalence all along, actually. If I had some combination of resistors in parallel, we could figure out what its electrical equivalent is, all that kind of good stuff. We know how to figure out what the electrical equivalent of voltage sources in series are, voltage sources in parallel, current sources in parallel, current sources in series. We've covered all of that stuff, okay? What we're going to be talking about today is something slightly new. So I posit to you all that this circuit, a voltage source in series with some resistance RS, is electrically equivalent to a current source in parallel with some resistance RS. if these two things, on the left-hand side, this is what we call a practical voltage source. This is called a practical voltage source because it behaves like a realistic voltage source like we might find in a battery or something like that. So it's no longer an ideal voltage source where the amount of current that's flowing out of the positive polarity terminal of this thing is infinite. That current restricts the amount of current that this voltage source can supply to an externally connected circuit. And on the right-hand side, we have a practical current source. Where in this case, the resistor is restricting the amount of voltage that might appear across the terminals of our current source, okay? So I am postulating here that these two things are electrically equivalent under specific conditions. And we are going to figure out what those conditions are by simply applying a load resistor here across the open circuited terminals of each of these sources, and then figuring out what needs to happen to ensure that VL is the same for both cases, IL is the same for both cases, and therefore the same amount of power is delivered for both cases. Okay. So for our practical voltage source representation of our circuit here on the left-hand side, what is our current IL equal to? VL over RL, definitely, but let's put it in terms of VS, RS, and RL. Because it's always going to be VL over RL, but that's not helping us relate things to our practical sources that we're trying to relate. VS over RS plus RL. All right. What do we have here on the right-hand side? What would IL be in terms of IS, RS, and RL? So we have a current source connected to two resistors in parallel, and we want the current flowing through one of the resistors. So I would argue this is a great place for us to apply current division. Right? So our known current IS will be multiplied by the ratio of 1 over the resistor we're looking for the current through, which in this case is RL, divided by 1 over RS plus 1 over RL. And what I'm going to do here to make the connection that we're looking for is I'm going to multiply this guy by RL over RL. I'm going to multiply this guy by RS over RS. And so what happens when I do that is I get IS times RL plus RS divided by RS times RL in my denominator. And then I have a 1 over RL here. This is slightly less bad, but it's not overwhelmingly less bad. But I have a fraction divided by another fraction. So what do I do when I'm dividing a fraction by a fraction? Multiply by the reciprocal, right? So this is going to look like IS times 1 over RL times the reciprocal of my denominator. That's going to look like RS over RL, or excuse me, RS times RL divided by RL plus RS. And we can see pretty easily that this RL cancels this RL, leaving us with simply IS times the ratio of RS over RL plus RS. So we have this thing for IL on the left-hand side, this thing for IL on the right-hand side. Under what conditions are these two things equal?
When IS times RL, or IS times RS equals VS.
You're exactly right. So when VS is equal to IS times RS, these two circuits are electrically equivalent. Now, we only proved it here to show that the current IL is the same in both. We could easily derive a relationship for VL on both sides of this equation. On the left-hand side, this would be using voltage division. On the right-hand side, it would be using Ohm's law, and we would find out that VL would be equal for the left-hand case and the right-hand case under this exact specific criterion as well. So whenever VS is equal to IS times RS, a practical voltage source and a practical current source are electrically equivalent, which means we can interchange them. This is a circuit analysis tool that we can use to potentially simplify circuits, okay? So there are some strict rules here that I want to talk about, okay? So we're going to go through just a couple of examples. If I have a practical voltage source that is a 10-volt source in series with a 5-ohm resistor, I can transform this into a current source in parallel with that same 5-ohm resistor. All right. So one thing that I want, excuse me, one thing that I want to point out here, and it's critical, the positive polarity terminal of our voltage source tells us where the head of our arrow is supposed to be, okay? So if the positive polarity terminal of the voltage source is on top, the arrow needs to be pointing up. If the positive polarity of the voltage source was on the bottom, the arrow would be pointing down. If the positive polarity terminal of the voltage source would be on the left, the arrow is pointing to the left. If the positive polarity terminal of the voltage source is pointing to the right, the arrow is pointed to the right. Okay. So what value should our current source, the independent current source on the left, have? 2 amps, right? Because this is governed by the relationship that VS is equal to IS times RS, or we could say simply that IS is equal to VS over RS, or we could say that RS is VS over IS. We're not actually going to use this one today, but it will come up with what we're talking about on Friday. Okay. So we can go back and forth between these two different forms if we follow this simple rule, which is just based on Ohm's law. And we have to pay attention to the fact that the positive polarity terminal of the voltage source corresponds to the direction that the current source is pointing in, okay? So let's take this gnarly looking circuit here. I have 5 amp source connected to a 3 ohm resistor, which is in turn connected to a 4 ohm resistor. Here I have 7 ohm resistor. I have a dependent source like so. One amp source. And this is the voltage Vx that controls our dependent source. Okay. Our goal here is to solve for this quantity Vx. Now, we can look at this circuit and see that it contains 5 meshes, which is well beyond what our calculators are able to solve. It has 1, 2, 3, 4, 5 nodes as well, which if we happen to have a Casio FX991 calculator, we could ostensibly solve this, but there would be an extra equation relating Vx to nodal voltages as well, so it would require some algebra to force us to be able to use that calculator. So what we are going to do is we are going to use this source combination technique to simplify this circuit in a form that's more easily approachable with our limitations, okay? So if we have a computer in front of us, this is kind of pointless. From purely a circuit analysis perspective, the computer can handle as many meshes or nodes as we can throw at it. But from a hand calculation perspective, this is a pretty interesting tool, okay? So how many practical sources do I have? So anytime I have a current source in parallel with a voltage source, I have a practical current source. Anytime I have a voltage source in series with a resistance, I have a practical voltage source. So I'm going to ask you again, how many practical sources do I have? 3. It does not matter that it's a dependent source whatsoever. That still counts as a practical current source up top. So as this circuit is currently drawn, there are no resistor combinations or source combinations that could be made to simplify it. But what we will observe is doing a few source transformations will allow simplifications to occur. So for example, I'm going to give us a pair of terminals over here on the left-hand side. We are going to replace everything to the left of this pair of terminals with its practical voltage source equivalent, okay? I draw these terminals for a specific reason. When I approach a problem like this, I effectively disconnect what I'm trying to transform from the system, do the transformation, and then connect it right back to that set of terminals. So that tells me where things are supposed to go. So in this case, if I disconnect my 5 amp source that is in parallel with my 3 ohm resistor, what can I replace this with? 15-volt voltage source. Anything else that comes along with it? A 3-ohm resistor in series. Does it remotely matter what order I put these elements in? Not at all. Okay. So if I replace this with its electrical equivalent, here's what I have now. So what did this operation do? Well, it eliminated a mesh, but it introduced a node. So it didn't really do a lot there from the perspective of variables in our equation. The big thing here that it did though, was it put that 3-ohm resistor and that 4-ohm resistor in series so that we can combine them now into a single 7-ohm resistance. So 3 ohms in series with 4 ohms looks like 7 ohms. And we've now eliminated both a mesh and a node from this system, okay? So we could perform a source transformation on that practical voltage source on the left-hand side if we wanted to. One reason why we might want to do that is it's going to put those two 7-ohm resistors in parallel so that we can combine them and eliminate yet another node and mesh. Okay. So 15 in series with 7 is electrically equivalent to 15/7 of an amp. In parallel with a 7-ohm resistor. So, and I want to make sure that that 7 looks more like a 7 and not like a 2. And now I can easily see that I have those two 7-ohm resistors in parallel. So that's going to look like what? 7 in parallel with 7. 3.5. Right? Anytime you have two equal resistors in parallel with each other, the equivalent resistance is just half. If we were so inclined, we could then do a source transformation here as well. So 15/7 times 7/2 is going to look like 15/2, right? And it'll be in series with 7/2 of an ohm. Let's leave that left one alone for a while now. Let's look at what we have over here on the right. What would I replace that equivalent, excuse me, what would I replace that practical current source with? 9 volts in series with a 9-ohm resistor. Absolutely correct. let's leave that one alone for now as well. And let's look at this practical current source containing the dependent current source that's connected at these green set of terminals, right? So what's that going to look like? Recall that V is equal to I times R. That's literally the rule we're using here. So if I is 3Vx and R is 17 ohms, 3 times 17 is 51. So our voltage source is going to look like 51 Vx in series with a 17 ohm resistor. I'm going to put the positive polarity terminal over here on the right where the head of the arrow was. 3 times 17, if my mental math is correct, is 51. And I'm just going to drop this 17 ohm resistor in right here. And what do we have now? A single loop circuit that we could have analyzed on the second day of class. So that big monstrous looking thing that we started with is electrically equivalent to this trivial thing that we can solve just using Kirchhoff's voltage law and Ohm's law. So this is where source combination, or excuse me, not combination, source transformations can be a very, very powerful thing, okay? What we are going to talk about in our next class meeting is Thevenin and Norton equivalent circuits, which is a more formalized rule for effectively making any two-terminal network look like either a practical voltage source or a practical current source. Okay. All right, so you may be asking yourself why and or how this might be practically useful, which is a pretty reasonable thing to ask yourself, okay? So if we had a very convoluted circuit and we were interested in determining how much power is delivered to a single resistor or something like that, we could use a practical voltage source equivalent circuit or a practical current source equivalent circuit to effectively do our power analysis on that much smaller scale circuit. So what we're going to talk about now is what's called the maximum power transfer theorem. And then at the end, we're going to tie these two topics together. So the maximum power transfer theorem answers the question, what is the maximum amount of power that can be delivered by a practical source. So let's say that we have a 10-volt source connected to a 10 ohm resistor. This is our practical source. And then connected to this practical source, we have some load resistance RL, where this is the voltage drop across our load resistance VL. And this is the current flowing through our load resistance, IL. Okay. We can see pretty easily that our current here, IL, is just going to be 10 volts divided by 10 ohms plus RL. And from this, we can say that the power that is absorbed by our load resistor, PL, is IL squared times RL, which looks like 10 volts over 10 ohms plus RL quantity squared times RL. So we have a power as a function of load resistance. If we were to plot this graph, it would look something like this. So this is power as a function of resistance. And this is the load resistance RL. At RL is equal to 0, there would be no power delivered to our load because we just have a short circuit. The voltage drop across the short circuit is 0, and so V squared over 0 is going to be 0. Way out over here, we are approaching an open circuit. And so we should see, so effectively when the resistance gets incredibly large, the resistor is behaving more and more and more like an open circuit because it is letting less and less and less current flow through it. Up to some point when, once we hit that infinite value, the power that's delivered to that load resistance is once again 0. And then in between, we have something that looks like this, but it should be more centered. I just can't draw well. Okay. So there's a couple of things that we can glean from this drawing. First of which is there is a particular value of RL at which maximum power transfer occurs. One single value of resistance will cause this practical source to deliver literally the most power it can absorb. Every other resistance value will have a corresponding. So let me think about how I'm trying to state this because it's coming out of my mouth and it sounds weird in my head. So effectively what I'm trying to say for this next thing is that if we were trying to figure out what load would deliver, let's say 10 milliwatts of power, and we knew that 10 milliwatts wasn't the maximum value, right? So let's say that this point on the vertical axis right here corresponded to 10 milliwatts. There are actually two resistances that satisfy this constraint, one of which will be below the maximum power transfer point, and one of which will be above the maximum power transfer point. I am pointing this out to you because you're asked questions and stuff like that in your homework. And this is a simple quadratic function that I expect you to be able to solve for the two roots that satisfy that power relationship, okay? All right, so this is effectively the system that we are dealing with, okay? So now let's look at things in a slightly more generic sense and derive how we figure out what that maximum value is. So in general, power delivered to our load resistor is going to be our source voltage Vs divided by Rs plus RL quantity squared times RL. We've already derived effectively where that came from. So if we want to find the value of RL that causes maximum power transfer, what do we need to do mathematically? How do we find the maximum value of a function? Take the derivative, set the derivative equal to 0, okay? So PL as a function of RL is, again, Vs over Rs plus RL, this whole thing squared, times RL. So we need to take the derivative of PL as a function of RL with respect to RL. I would argue that this looks like Vs squared times RL over Rs plus RL squared. The reason why I put it in that particular form is so that we can use the quotient rule, right? Now, it's been 10 years since I've used the quotient rule, so somebody tell me what it is. Okay. All right, so I'm going to write down what I believe Daniel told me. So let's just say that we have a numerator that is a function of x over the denominator that is the function of x. The derivative is the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator over the denominator squared. Okay, that seems correct to me. I remember it being something very similar to that. So what's the derivative of the numerator here? Vs squared. And then the denominator is Rs plus RL squared. What's the derivative of the denominator? And then we multiply by the numerator squared, which is, excuse me, that by the numerator, which is Vs squared times RL. And then this is going to be Rs plus RL squared to the fourth power. All right. And we want this thing to equal to 0, which means effectively we don't actually care about what the denominator is doing, the denominator of this new expression at all, right? If the numerator is equal to 0, this thing's going to be equal to 0. So we have Vs squared times Rs plus RL quantity squared minus 2 Vs squared RL times RS plus RL. And we want this thing equal to 0. It's pretty obvious that there are common factors of VS squared in both terms that we can get rid of. So let's FOIL this thing out just a little bit here. So RS plus RL quantity squared is going to be RS squared plus 2 RS RL plus RL squared. Then we're going to have minus 2 RS RL minus 2 RL squared is equal to 0. I believe this, we'll use a different color. This bit and this bit cancel each other out, leaving us with RS squared minus RL squared is equal to 0. So what's our solution? When RL exactly equals to RS, we have maximum power transfer. So this thing right here, this particular value, when RL is exactly equal to RS, is what forces maximum power transfer to occur. Sure.
So the VS squared, where did the other VS squared go? You said VS squared minus 2 VS squared. Should there be a negative V?
I divided both sides by VS squared.
Okay.
And so 0 over VS squared is still 0. So I just took that common factor out and it doesn't really do anything. Any other questions? I have not actually derived this by hand in 5 years. So I'm pleasantly surprised that it worked out the way I expected it to. So we have applied a little bit of calculus to figure out that the only way that this criterion is satisfied, the maximum value for our power will occur when RL is equal to RS, okay? If we plug that relationship into our power equation, what we find is that PL max, and I'm going to put in parentheses here to let us know specifically what's happening. So this occurs when RL is equal to RS, is given by VS over RS plus RS quantity squared times RS, which simplifies to VS squared over 4 RS. So this is the maximum amount of power that a practical voltage source can ever provide. And it depends on the value of the voltage source itself, as well as its internal resistance. What do you think would happen if we had a current source? Practical current source in particular. Since a practical current source is electrically equivalent to a practical voltage source, we could simply substitute our relationship that VS has to equal IS times RS into this thing. And we would find that for a practical current source, PL max, where RL is equal, RL is equal to RS, would give us the relationship 1/4 IS squared times RS. We could either derive it, or we could simply say that VS is equal to IS times RS into our practical voltage source equation and get the exact same result, okay? So maximum power transfer always occurs when the load resistance is equal to the internal resistance of the practical source. And these are the equations that tells us what the value of that power will be. So now let's tie this concept together with our source combination concept, okay? If I have the following circuit, what I want to find out here is number one, what value of RL will cause the rest of the circuit to deliver the most power and number two, what is the most power that RL can absorb. So what we're going to do for part one of this question is use our source transformation techniques until we have either a practical voltage source connected to that load resistor RL or a practical current source connected to that load resistor RL. And then once we have that, whatever that RS is for that practical source tells us the answer to number one. And then the answer to number two requires us to know that RS so we can simply plug it into our maximum power transfer equation, okay? So tell me what to do. Let's apply what we've learned today. Okay, so we're going to change the voltage source into a current source. So what Brody is suggesting, and I'm going to go into a little bit more detail than his description, is we disconnect the practical voltage source that I have set aside here with these pink terminals and turn it into a practical current source. Reagan, what should our practical current source be? So this transformation is governed by Ohm's law. So if I have 12 volts in series with 3 ohms, I should get 12 volts over 3 ohms in parallel with 3 ohms, right? So 12 volts over 3 ohms is 4 amps, yeah. And I need to put this in parallel with 3 ohms. All right. So what can I do now? Mason. Okay, so 3 in parallel with 6 is going to be what? Which is 2. Jake, what can I do now? The 7 up top. How?
Oh, wait, no, yeah.
Okay, so we're going to transform our practical current source into a practical voltage source, which would in turn place the 2 and the 7 in series. Okay, so tell me how to do that. Tell me how to change this practical current source into a practical voltage source. This transformation is governed by Ohm's law, something that we learned on the 3rd day of class. V is equal to I times R. So we have I is equal to 4 amps, R is equal to 2 ohms. So 4 times 2 is 8 volts. All right. So 8 volts. Positive polarity on top in series with 2 ohms. Mr. Finch, what do I do next? Okay, so 2 in series with 7 is 9. Am I done? Yes, because I have a practical voltage source connected to my load resistance. So all I needed was either a practical voltage source or a practical current source, okay? So everything, you're not going to be able to see that. Everything that I've boxed in here in red is the practical voltage source that is electrically equivalent to everything we had before. So what value of RL will cause maximum power transfer to occur? 9 ohms. What is the maximum power that RL can absorb? So what's V squared here? So 8 volts squared over 4 times 9 ohms is equal to P max 64 volts squared over 36 ohms. So let's see, 64 over 2 is 32. 32 over 18 could still be, I should be able to do this math in my head better. Let's see, so 32 over 4 is, sorry, 32 over 2, 16 ninths of a watt, if my mental math is correct. Should have been able to do that faster. But anyway, this is what I expect you to be able to do with this material. If you look on the practice exams and all that kind of stuff, the very last material, by the way, this is the last material for exam 1. So the very last problem or 2 will literally be something like what we just did right here. I will have a circuit. I will ask you what is value of RL will cause the circuit to deliver maximum power, and then ask you to calculate what that power is. All right, I am done yammering for today. Yes. So let's answer that question real quick, okay? So Mason asked, would it be the same thing if we had done a further source transformation here? So this would be 8/9 of an amp in parallel with 9 ohms. So we would have 1/4 times 8/9 of an amp squared times 9 ohms. So that's going to be 1/4 times 64 over 81 amps squared times 9 ohms is going to be 64 amps squared times 9/4 times 9 times 9, these 9s cancel out, 64/36, yeah, it has to be the same thing, they're electrical equivalent, but I just wanted to go through and formally prove it, so yes. It does not remotely matter whether you wind up with a practical voltage source representation or a practical current source representation. Because they are electrically equivalent, they are only capable of delivering the exact same amount of power.